If I have time, I'll delete those things and I'll upload. But if I don't have time, please ignore the ChatGPT slop a little bit. Yeah, I guess I have just stuck to my old slides, but they were, pre-LLM days slides. So you know how that is. It's a plain white background and just text and images and typical PowerPoint slides. I thought I can experiment a little bit and update the infographical style. Um, but I guess it was not like a few hours job. I think it's like a big job. So it might take a days to do that actually. Okay. So this is where we were last week. We were trying to find what is wrong with, we were trying to convert text to embeddings basically, or represent text in some mathematical form, number form, because neural networks only understand numbers. Because neural networks understand only numbers. So in a nutshell, actually, the numbers and AI, sorry, the text can be converted to numbers with meaning or without meaning, right? If I'm going to convert uh, if I'm going to convert text to numbers just randomly without giving importance to meaning or context, that's going to be called sparse encoding. And if I'm going to And if I'm going to convert my text to numbers with the context and with some meaning embedded into it, then I'm going to call it dense encoding, okay, or dense representation or dense embeddings, dense features. Sparse is just basically converting my text into numbers with minimal or no context or meaning, right? So, for example, one hot encoder. Technically, a text data is basically only categories. Like, for example, I think we did it in the last class. If there are 50,000 words in the dictionary, I can just assign one number to each word, and I can just do a one hot encoding. Of course, that would create 50,000 new rows, but that's okay. It's just like dealing with 50,000 products in a big enterprise or company, right? But the problem is words are just more than text categories. Okay. When I say cup, right? And when I say jug, and when I say bottle, when I say container, mentally we are mapping these things in a, I mean, we know that these things are similar or they perform a similar function, right? Um, and that actually helps in language, that helps in processing natural language. So just converting text into meaningless, contextless numbers is not going to help us get the best the out of the text, right? So we aim for converting the text into numbers with some context. That's where the concept of vector comes into space, right? So a vector is basically, I mean, a one hot encoded category is basically a vector, right? So if I have, let us say, um, if I have mat, and if I have door, and if I have table, okay, and let us say I have different categories for this, right? So this is after one hot encoding, this will become something like this, and this will become 0, 1, 0. and this is going to become 0, 0, 1, right? So, so even my one hot encoding is kind of like a vector, but the zeros and ones, where the one is sitting, where the zero is sitting, that doesn't really have any context. Like if I'm going to move door to here, right, and mat to here, I can still retain this technically, right? So there's no real meaning, and that's why it's called sparse features, right? Um, Sparse features works for small documents for simple tasks, but when the task becomes too complicated, then sparse features are not really the way to go, right? One way to do like how we did in our ML algorithms is we can actually define the features and the feature representation. Like in the sense, I have, let's say, a corpus, like a text corpus, and I want to get something out of it, right? Or I can, if I want to just understand what that corpus is about, right? What can I do? Without now, imagine that you don't know anything about neural networks or any of these embeddings or LLMs or anything. Okay, I have a corpus. I want to know what that corpus is about. What is the simplest way, or how will we as humans, when we look at the text corpus, how will we process it? Sorry, am I audible? I just jumped into the topic without any warning.
Yes, we can hear you.
Okay. Yeah. So my question is, I have a text corpus. Um, how will I know what it is, what it's about?
And based on prior understanding, we classify.
Yes. Okay, based on prior understanding, or let's say, it's complete jargon to me. Let's say, my second grade kid is looking at a textbook on deep learning. What will they try to find?
Relate to what they know.
Relate to what they know. Yeah, correct. One of the things that we can actually do is we can try to find the frequency of association. Yeah, association with what's already there. But one of the things that we can actually do is we can try to find the number of words which occur very frequently, right? That is a pattern. I mean, I might not know what the word might actually mean, but I'll at least know that, okay, this is a word that has come maybe, 10 times or 20 times in this document, right? So that is one type of feature representation. So this is like, I am telling the algorithm what to do, right? So that is the human defined representation. Okay. So instead of just doing a one hot encoding, I am, trying to make some sense of it by finding a term frequency, right? So that is TF, or term frequency, which is again a sparse feature, because really that doesn't really bring out the true nature of the word, right? Another way I can look at it is, what are the words that usually come together? For example, the word deep might always be followed by the word learning, right? So that is actually related, right? The word deep, learning, and train can always come together, right? So that approach is basically finding what words are occurring with what words more frequently. That is what's called bag of words, or BOW. Okay, bag of words. Right. So the point I'm trying to make here is before we jump into LLMs and embeddings and all that, people have been using text processing. People have been converting data into meaning, some sort of text represent or number represent numerical representation, and have been calling it encoding, right? And there are different ways in which people have been doing that. Bag of words, term frequency, inverse document frequency. So they are what are called sparse features because there is no real context or meaning, deep meaning associated with a particular word, right? We define, like how in manually we thought PCA will help. So we've engineered that feature, right? We thought taking a log of this of a particular column will help. So we did the feature engineering, we did the transformation, right? In text also, this is the feature engineering, right? So we try to find meanings and we say, okay, maybe the number of times a particular word comes is important. Maybe the association of one word with another is important. So we came up with something called bag of words. And then we thought, maybe one word is not always important because, deep learning, although they are two words, they are actually, it's like one word, right? So that is n-grams. How many times a word is going to come with another word? Okay. So that is 2 grams or 3 grams or n-grams. So so people actually engineered these features where humans define these representation, that is sparse features. Okay. So the learning of relationship is purely based on how the humans are defining it, not on any semantic relationship between the words. Okay, that's why it's called sparse. Now there is another thing called dense. Okay, dense embedding, dense encoding, dense vectors. That is basically where the neural network is going to shine, right? So we are going to give the data to neural network. We are going to define some sort of a way to, we'll look at it deeper, some sort of way to start with converting text into number, and then let the neural network define the semantic meaning, right? And the different context in which it is going to come. Like, for example, let us say the word, cat. Now, the word cat is an animal, right? The cat is also a thing that might be associated with the word mat, right? The cat is sitting on the mat. The cat is sitting on the table. The cat is sitting on the sofa, right? So, or cat can also be associated with the words that sound like animals, right? So the word cat sits in the world of animals. It also sits in the world of household items, right? Now, the embeddings, it can actually learn, okay, how does the word cat sit in the overall corpus of the language? Like how many words it can sit in, how many feature spaces it can sit in, right? Once we bring that into the consideration, suddenly the vector space for the word mat stops being meaningless and it now starts getting something like mat in the world of household items. It has a score of 0.53, right? And in the world of something else, it has a score of zero point 0.2. In the world of something else, it has a score of 0.97 and so on. How many such words we want to create is like up to us, right? So the door, again, in the world of household items, this has a score of 0.4. Okay, in the world of office items, it has a score of 0 0.4 again. In the world of ocean, it has a very low score. right? So suddenly these numbers, they are not sparse anymore. They have become dense in the sense it carries some meaning with it. And those meanings are learned from the corpus that the basically from the corpus, right? This is where the neural networks come into picture, right? We show the corpus to neural networks and we let the neural network figure out these numbers. Okay, that is dense representation or dense vector. Okay, if we are able to understand these two, the sparse representation and some of the algorithms there, and the dense representation, some of the algorithms there, I think the first part of the lecture is almost done. Yes, Sunil.
So just to clarify, when you
Yeah.
say dense, through your example, did you mean that it doesn't necessarily need to have a high score in terms of the correlation with that particular context, but have the relative score with a variety of different contexts that it could relate to? And because there's a variety of different contexts, irrespective of the strength or the score, it qualifies as dense?
It qualifies as dense because the number has a significance, right? These numbers are completely my inventions,
Yes.
right? The actual numbers we will never get to know. I don't we know we don't know what those numbers are. It's completely irrelevant for us also,
When
right?
you say numbers, are you referring to the scores?
The numbers which I have assigned here,
Got it. Got it. Yes.
these
Okay.
ones.
Got
So
it.
dense basically means that we create those we we let the neural network learn its place in the overall corpus, world of corpus.
Hmm. So essentially, it's increasing the context and therefore becoming dense.
Yes, in a way. We'll come to that.
Okay.
How these neural networks are trained and what happens. We'll come to that in a minute.
Okay. Thank you.
Yeah, Atif.
Yes, so I don't have a technical background, so I'm going to make it a little bit simple and you tell me if my simple representation is correct. So you use the example of dogs and cats. So dogs, for example, they bark, cats meows, and then you're assigning numbers to dog, cats meowing, and they're barking. And somehow you're saying that uh, the meowing and barking gets embedded into the same vector space because there is some pattern there.
So what I'm saying is a cat can be associated with a number of things. A cat is an animal. A cat can be a pet. A cat can make a sound. So the three things that we discussed here, as in the animal space, a cat has a score, right? In the household items, its relationship with the household items, it has a score. In its relationship with the sounds, it has a score, right? Now, the score it has a meaning, right? So, for example, the word meow is probably very strongly associated with cats than with any other word, right? So that relationship, that semantic relationship is captured through these dense encoding. Whereas the word dog can be associated with cats, but it's the strength of its association is not as strong as the word meow.
Okay, and the association is partly determined by the grammar. I mean, we're talking about cat is a subject, dog is a subject. So that is
Ah.
also playing a role.
So it's not like in terms of how we understand English language. like if you want to take that example, the word was, right? Was can be associated with any word in the in the English corpus, right?
Right.
So if I say was, not VAC, WAS, was, I mean I have no context, right? I can't link it with one particular word. Probably just tense, past tense. That's the only thing I can relate it with. So the word was will probably have more association with anything related to tense and anything that happened in the past than to any particular object or subject.
Okay.
Right?
Okay.
When
That's
we
what,
show show sentences to neural networks, the neural networks basically learn those associations.
got it. And one clarification. So I think you guys briefly talked about it that in hot encoding, there's a programming involved. But in this case, when we are assigning numbers, we are helping the neural network to represent reality internally, correct? Is that the right way to say it?
Correct. Yes.
Thank you.
Yeah. Okay. So moving on. Okay. So I have a separate slide deck for this. I'll come to that. Session. Okay. So I'm going to spend a couple of minutes on how some of these old algorithms which do sparse encoding, how they work. Okay. How they work. Okay. I hope you can see the full screen version more of the slides now. So let us say that there is a corpus. Okay. And I have 3 documents. I have 3 documents. I mean, this is a toy example, right? So the document 1 is just the cat sat. Document 2 is the dog sat. And then document 3 is the cat slept. Okay. Our goal is to convert the text into some machine readable representation, right? Which is kind of the goal of the class. Now, the first step is what's called tokenization. So I'll talk in detail about tokenization in a minute. But for now, let us just understand that I'm going to convert every word into some number, some randomly assigned number. Okay. So every time there is a space, I'm going to consider that as a token. Okay, that is my rule for tokenization for this particular case. Okay, I will refine this definition later, but for now, my definition of a token is basically every time I come across a space, I'm going to consider that as one token. The token is basically the smallest part of the corpus that can be individually fed into a machine. Right? So here I've made my rules simple. I said every time there is a space, I'm going to consider that thing as a token, right? So obviously the cat sat are 3 tokens. So totally I have 9 tokens in this whole document, this whole corpus. Now, what happens is when I build my vocabulary, okay, the algorithm basically scans all the tokens and it keeps only the unique words, right? This is how bag of words really works. So I'm starting with an empty slate. I'm the algorithm is basically seeing the word the for the first time, adds it, cat sees, adds it, sat adds it. Now it comes to the second document or paragraph or whatever. Okay. The word the already exists, so it is not adding it. Right? The word dog has not occurred, so it adds it. The word sat already exists, so it is not adding it. Right? Similarly, for the third document, the cat slept. The and cat already exists, so only slept. The word slept gets added. So it encountered the cat, sat, dog, and slept. So internally, it has built a vocabulary with these unique tokens. Right? Now, each of these gets an index. The index is basically a randomly assigned number. This is where the difference between sparse and dense really comes out, right? There is absolutely no reason cat should get 0 and dog should get 1, right? If my first corpus had been that dog sat, then probably dog would have gotten 0 and cat would have gotten 1. So there is no meaning to that. Each unique word gets assigned a particular index or some ID. Right? And then something called a bag of words vector. Bag of words vector is created. So if my document says the cat sat, from my vocabulary order, okay, cat gets 1, sat gets 1 because it occurs once, and the gets 1. So the bag of words vector is 1 0 1 0 1. This basically only means that the word cat is associated with the word the and the word sat. Now, if my document had been the cat sat, okay, the cat sat, the cat slept, right? If this is my my corpus, now my bag of words would be cat would be 2, right? Cat would be 2, dog is 0, sat would still be 1, the would be 2, and slept would be 1. Right? This still has some meaning, right?
Can you explain it one more time? Because I didn't get why 0.
Because the word dog has not occurred in this vocabulary at all, in this in this document at all. Okay, so till step 3, it is training. It is pre-trained and it has all these index and it has built its vocabulary. Right? Now, a document comes, right? When I say document, it is actually the unseen data, right? The data that it is getting in order to do a particular task. Let us say I want to know what this document is about, right? So when it sees new data, based on the vocabulary that it has built here, right? It is doing a basic frequency count of what words are occurring with what. So now this has basically learned that the word the, okay, is associated with the word cat. Why? Because this occurs twice and the word cat also occurs twice. Right? So this algorithm, bag of words, basically tells us how frequently a word occurs with another word. Is that clear? Okay.
So, Professor,
So,
just to
yeah,
clarify, in simple language, going back to what you said before, what corpus we choose determines what aspect of reality it's going to see.
correct.
Yeah.
Yes. So this is my training data. This is my training data. The one you, yeah, document 1, 2, 3. This is my training data. Okay. This is my unseen data or my, yeah, my unseen data basically. Right. You see how this is still a vector, right? But this is still a sparse vector. There is some meaning to it, but we have basically given some meaning to it rather than it has learned it on its own. Yes, Suvesh.
So is the objective still to try and identify the strength of the association?
Yeah, so before all these algorithms, I'm just trying to explain the difference between sparse and dense. And these are pre-LLM algorithms, right? So pre-neural network algorithms. The goal is to see, the goal is to understand text in some form, right? At this point, we are just thinking, I mean, ideally, I would want to find the semantic similarity. But the first step towards that is finding what word occurs with what word more frequently within a corpus.
Got it.
Yeah, Nimish.
Yeah, Professor. So let's say if the next sentence is the dog sat. So in that case, the number would be 3, 1, 2, 1, 2. Is that correct?
So you say that
The
the
dog
dog
sat.
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 Okay. So
So
now
then
this would
it
be
would be
3
3.
and dog would get 1
Mhm.
and sat would get 2.
2.
This is still 1 and this would
And
be
that
2,
would
I
be 2.
guess.
Okay. Yeah. And
Right?
what if the next sentence is the dog and cat sat? So we add a new word and what happens then?
It is not a part of my training, right? So it will
Okay.
not know what to do.
Okay. Got it. Thank you.
Okay. But you see how this is even powerful at this stage, right?
Mm-hmm.
So dog and cat usually comes together.
Mm.
So some meaning is coming out that, eventually we will probably find that they are animals or pets or uh, household pets, something, right?
Mm-hmm.
So some meaning really comes out of this, but not at the scale at which we want,
Okay. Got it.
right? And you see the word the is almost associated with everything else. So people would really get rid of the things like the, was, is.
Mm.
They are called stop words. So we're just going to get rid of that because that just messes up my algorithm completely.
Yeah, it just adds into the complexity unnecessarily.
Unnecessarily, yeah. And there
Got
is
it.
not one word that I can really associate that with.
Mm. Okay. Thank you. Thank you.
Okay. Yeah.
Yeah.
Okay. So that's basically, yeah, Atif. Yes.
Sorry, just to clarify, I'm just trying to look at it from a very high level. So the model is looking at the cat walked the dog walked, humans walk too, right? So at that point, there's an association between all three, humans, cat, and dog. But then human does something that cats and dogs don't do. For example, human, I don't know, voted. So that will create a separate vector space for humans. Is that how the neural network is thinking? Because human did something that cats and dogs
We'll
didn't do?
we'll come to how neural networks work in a minute.
Okay, thanks.
Okay, this is pre-neural network time. Okay. Keep the changes. And stop share. Going back to my okay. So this is where we were. So one hot encoding, I mean, we discussed this. So as I said, these are slides from the vocabulary order is crucial here. How is it crucial here, the vocabulary order? What do you mean by vocabulary order? Jeff?
Well, it sets the vector, sets up the vector.
Yeah. Oh, okay. So yeah, so the numbers within the vector for that particular training, the place where the number occurs, that is crucial given that particular vocabulary. So it has built an internal representation of the vocabulary. In that, cat takes the first place, dog second, sad. So and the numbers that are assigned to it is mapped with that. So in that sense, it is crucial. But the actual token IDs that cat gets, that is completely random. Right?
Okay.
Okay. Okay. So we saw the problems with one hot encoding. I don't think I need to explain it again. Yeah, so one hot encoding basically increases the cardinality of the data. This might slow down training, but more importantly, the similarity is really weak because the distance between cat and dog would be the same as distance between cat and ocean, maybe, right? Or cat and water. If you know, cats don't like water. So um, figuratively and literally, the distance between cat and water will not be truly represented if we use one hot encoding, right? Bag of words is another approach, another way of sparse encoding. So let us say my vocabulary has these words, surveys. The service was excellent, but the delivery was late. So as you can see here, my vocabulary only has service, excellent, delivery, late. We have successfully gotten rid of words such as the, was, but. We are going to call them stop words. And as I said, they are going to increase the complexity. So we got rid of it. Again, my vocabulary has 4 words. The document vector has only the counts. The order is really ignored. It really depends on which sentence came in the corpus first, right? So actually, bag of words is pretty powerful if you want to do some quick baseline and see if this corpus is worth using or finding if anything will come out of this project, right? So for that, bag of words is really good. But of course, this has its own limitation. For example, good, not late would be represented the same way as not good, late, right? The meaning is completely flipped actually, right? So bag of words can never bring out sentences like this, filled with sarcasm, filled with nuance, and things like where the stop word is going to be important, right? So things like that will never come out when we use bag of words. TF-IDF. So TF-IDF is basically, I mean, bag of words is basically one form of term frequency counting. TF-IDF is IDF basically stands for inverse document frequency. So TF, how often a word occurs in a document as a function of how rare that word is across all the documents, right? So it really brings out how rarely a word is going to occur in a particular document, right? So this really helps us in understanding clustering, where a lot of words come together, where there is also some unique word occurring, right? So all this you can find out using this thing called TF-IDF, inverse document frequency, term frequency, inverse document frequency, right? I'm going to really skip this. Okay. And move on to how some pre-processing steps that are involved. Okay. So these are some of the sparse encoding techniques. Before we go into dense encoding techniques, dense embeddings, neural networks, how neural networks look at these things, I want to spend some time talking about some pre-processing steps which are common for almost all text processing pipelines. I want to pause here and ask if there are any questions.
So, Professor, I have one question.
Yeah.
So, in the sequence of slides from one hop to back of web and also the IDF, is it one better the other, or they have specific characteristics to cover another's short the disadvantage of each other?
Yeah. So these things, they basically work on how frequently a particular word is coming, right? And again, this is a human engineered feature, right? So people sat with the document and then they saw, okay, if a word occurs more frequently, then that is probably a very important word. And that really brings out what this document is about. So one of the simplest things you can do is start finding which word occurs the maximum, what word this particular word co-occurs with, right? So these are very simple techniques which existed before we had these mammoth neural network based embedding with our LLMs, right? They are still powerful. When we start with a small corpus and we want to do some basic understanding of what the corpus is about, we can still use these algorithms. Actually, I mean, it's just a library call, and we can do it in like 15 minutes max, right? It gives you an idea of, is this project worth taking? How long? How complex is the project? How much time should I give to complete this project? Now, if you want something very basic, we can still use any of these. So it's not about one thing led to the other. This is better than the other. Each one has its own strengths. That's what I'm trying to tell here.
Professor, one question.
Yeah.
When we try to tell about like what are the other words appear and so on, we try to encode that particular word in relation to the other co-appearing words. Is that correct? And when it comes to
Yes.
the TF and IDF, they are basically a metric rather than a code. Is that correct?
And a score, yeah, correct.
So it cannot be used as a code, CODE, but it can be used to arrive at a code. Is that correct?
It can be used to arrive at something like this, like a vector representation.
Yeah, it can be used to arrive at something. Okay, so
Correct.
based
Yes.
upon like we can give something like so it is basically serving as a kind of a probability metric and what has to be prioritized and what has to be deprioritized, right? Like when we
Yeah.
say IDF, we say that okay, this particular value occurs in this document, but it is rare in other documents, so this has to be prioritized. Is it correct understanding?
For this particular document, yes, correct.
Thanks, Professor. Thank you.
So, Professor, can we group all of these above we just discussed about as a term under embedding techniques? Is it correct?
Yeah. So that is strictly, we can call it embedding, but the better thing would be to use the word sparse. Okay. So as long as you use the word sparse, we can call it sparse features, sparse embeddings, sparse representation, right? So the word sparse sits better than the word embedding.
Got it. Thank you.
So the reason why you prefer sparse is because except for few of the columns, every other column happens to be zero, whereas in embedding, it happens to be a numeric number ranging between 0 to 1. Most of them will have a non-zero number ranging between 0 to 1. Is that correct understanding, Professor?
In a way, actually, the word sparse and dense, it's related to more the number of the way that we understand these words rather than how many numbers we assign in that vector space, right?
Okay.
So if I do one-hot encoding and my document has like 500 words, it is actually a 500 word vector, right? That doesn't make it dense. It is the word, it is understanding the context of the word that really makes it dense. The semantic meaning rather than some shallow stuff like how frequently the word occurs.
So my question was from this particular context. I am just trying to confirm this. If I am suppose embedding a word in a 128 domain space, and if I'm looking at all that 128 vector, so it is technically, it is identifying or embedding that particular word in a 128 dimension vector space. And now if I'm looking at the coordinates of that particular word, it will be in a space like if we see that 0.28, 0.58, 0.60, 70, something of that sort. So which tells something like it is not at origin and aligned to the basal vector direction. When I'm saying that basal vector direction, most of the dimensions are the zeros and one is one or whatever it is. But whereas, so because of that, it doesn't become a sparse vector. All the dimensions are containing some value, and because of that, those dimensions
more than value, it has a meaning. That's the only change I would want to make.
Yeah. But whereas when we try to look at these kind of representations, like what we see is that except for few of the dimensions which are having absolute ones, the remaining are zero. Can I interpret that way, Professor?
Okay, I'll explain it like this. Okay.
Sure.
The corpus that we had, right? Let us say that the corpus actually has 128 words. Okay. The same example that you are using, the corpus has 128 words. Exactly like the dimension space of the dense embedding. In sparse embedding, I can fill the vector by giving numbers such as, by giving numbers which represent the term frequency, which represents the term frequency, inverse document frequency, DF, IDF. So these numbers are still 128, right? So I can do 5, 8, 9, 10, whatever, right? I still have 128. Whereas in dense encoding, okay, the 128, each number has each number is learned, okay, and it is a meaning in the overall corpus. Okay, one of it can be engram as far as the neural network is concerned, because we let it train, and I'll come to that in a minute. Okay, one number can represent how frequently this occurs. One number can represent how frequently this occurs in this particular paragraph, right? One number can represent how frequently this occurs with some other word, right? So we don't know what those 128 values are, but there are 128 dimensions to that word. Here also, a lot of these dimensions could be 0 because the word ocean might be related with the word sand or peace or calm, but it need not be related to the word laptop, right? So the laptopness or the electronicness score could still be 0 for the word ocean. That's what the neural net learns. It learns the semantics of the word rather than just shallow things like frequency.
Got it, Professor. So it associates with the meaning rather than the what I can say, the probabilistic properties of it.
Correct, exactly. That's why the word, the 128 number, it really doesn't have any meaning, or the number of zeros in it, it doesn't really have any deep meaning.
Yeah, this part I understood, Professor. And what I was trying to get is about the sparse and dense when they both use 128 dimensions.
Okay, now it's clear?
Yes. This part is clear. Only thing is
Okay.
I'm trying to understand that sparse and dense part. You're getting it, because like if both of them using 128 dimension, even in the current this one, or I just want to clarify this part. Now, when
the 128 in sparse could just be that there are 128 unique words in your corpus. That's all.
Okay.
Whereas in your dense representation, it could actually mean 128 contexts or 128 dimensions for that word.
Got it. So it is almost something like it's a difference between a one-hot encoding and a kind of numerical encoding sort of it. Something equivalent to, but I mean, not in the right sense.
Okay.
Yeah. Thank you.
Okay. So any text pre-processing starts with a basic step called tokenization, right? So if I have something like the service was excellent, but delivery was late, okay? Tokens are basically the input unit which goes into any training module. It could be neural network, or it could be bag of words, or it could be DFIF, or anything. The smallest unit that goes as input is going to be called token. Mostly in bag of words and all that, it's going to be a single word. Okay. The embeddings, they basically turn those units into dense vectors or sparse vectors, depending on what approach we are taking. When we do neural networks, the neural network actually learns the patterns across these vectors. So we can do different types of tokenization. We can do a word level tokenization where if I say chatbots are helpful, chatbots are helpful. These are each one is one token. We can do character level tokenization where every character becomes a token. The most common in LLMs is probably subword tokenization, where a word is split into its smallest units, right? And that is given as token. Now, why this is advantageous? Again, the last line is a little bit of AI's law. So why this is important is unhappiness. You can make a number of words using these smallest units. I can say uncanny. Okay. I can say understand. Okay. I can say, give me a word with ness, harness, or something emotional like happiness, sadness. Okay. Sadness. So now what happens is if I break the word into sizable parts or reusable parts, I can basically say, okay, now unharness, right? So the ness is usable, reusable. The un part is reusable. So the actual emotion of the word is actually the middle part, right? Similarly here, the first part. At a word level tokenization, I might miss these nuances, right? Now I can actually make up things like bottleness, right? So when I say bottleness, somehow, although it is not a word, we can kind of understand what people mean by bottleness, right? When I say the bottleness score of the laptop would be 0, the bottleness score of the jug is 0.8. This sentence might actually make sense to humans, right? But if I give it to an algorithm that is trained on words, full words, it will not understand what is bottleness. But when it is trained on subword tokenization, it will guess the meaning just the way that we are able to guess. Why? Because it understands the word ness and it is associating it with the previous subpart of the word, right? So that's mostly why subword tokenization works in most cases. Okay, so tokens are basically the smallest inputs which go into an algorithm, neural network or otherwise. And the last is n-gram tokenization. So this also, n-gram is basically how frequently a word occurs with something else. Like for example, deep learning. Deep learning is actually two words, but it is one meaning, right? Deep on its own means different. Learning on its own means something different, right? But deep learning is actually one concept, one word. So sometimes giving that as input actually helps, right? That is one tokenization choice. Okay, clear? I think I explained this.
I think it's somewhat clear, Professor. This is my first time hearing this explained. So it's somewhat clear to me, but I would not say it's totally clear. That makes sense. I need to, it's the first time I'm hearing these terms and this explanation.
Okay. What we will do is just bear with me until the end of the session. If things are still very murky, let me know.
Thank you.
Okay. So in short, tokens are the smallest input units to, let's stick to neural networks, to the neural network. Okay. For learning, for training or whatever. Okay. The question is, at what is the level at which we are going to input to the neural network, right? The easiest would be to input each word, but the word level tokenizer might not work in most cases. So it would be good to break a word into multiple parts, right? And that actually helps in improving the performance of the neural network, right? So that is subword tokenization. We break a big word into smaller units, and each unit is fed as one input token. Okay. I guess if this is understandable, we are good. Okay. And before even we do tokenizer, some pre-processing steps. We talked about one pre-processing step, which is stop word. So a good practice is to remove stop words such as the, was, but, is, anything that can be related with any word in the English language. And now the next one is what's called stemming. So stemming and lemmatization is basically converting a word into its root word. Like for example, jumps, we convert to jump. Children, we convert to child. Like for example, running, ran, runs. What else? Okay, all these three words, they relate to one word called run, or run, even run. Right? So stemming and lemmatization, they are processes. We'll understand this more when we do the lab actually. Is basically converting all these words into their root word run, right? So that it's easier to process those words, so that the algorithm basically understands that these four are not four different words, but they just mean one thing. Okay. A question in chat box. At computational energy cost, trade-off between meaning, accuracy, and tokenization levels. Exactly. Yeah. So that is something that we did not talk about. If we do subword tokenization, the compute cost, the resource requirement actually becomes much, much greater than word level tokenization. So that is something definitely to consider. Right. Yes. Completely. Okay. So when will it matter when we convert this kind of conversion, where we convert, where we do stemming and lemmatization? When would it matter? And when would it have any negative impact? Let's say we are translating a corpus from one language to another, right? So if we do extensive lemmatization and extensive stemming, then the tense is going to be lost, the tense information. So translation might not look good. So it would be good to retain the tense and all that when we do stuff like translation. But when we want to do something like sentiment analysis, it's okay to do some sort of some level of pre-processing, some level of lemmatization. So the correct pre-processing actually depends on what task we are doing, rather than arbitrarily doing a pre-processing step, which is slightly different from what we discussed till now in neural networks, because we just said or now just use ReLU, use sigmoid, use batch normalization. So we just gave these prescriptions, right? So that kind of prescription is not going to work for pre-processing text, right? It is mostly job dependent, task dependent. So as I said, stop word removal, it's good to preserve in some situations. It's good to carry the meaning in other situations. Okay, so stemming is basically cutting short the word. So if I have the word happily, um, probably the word ILY, right? Okay, the word ly is probably associated with a lot of words. So we can come up with rules where we say, okay, if I see anything happily, sadly, quickly, I'm just going to get rid of the ly because that doesn't really carry any meaning. I mean, if I say quickly or quick, it's not going to make much difference, right? If that's my understanding, then I might get rid of the uh, the end part. So I'm just going to cut the end part of it. So that is stemming. Lemmatization is basically converting something into its root word. So it requires, again, it can be rule based. So when I actually pre-process, I would tell the algorithm running, like in Python, you can define a dictionary, running, ran, run, runs, all this should be converted to run. So like this, I will define rules for a number of things. Okay, so if I have something like orangish, reddish, okay, stemming would be removing the ish. My understanding is the ish is not going to give me any new meaning more than just the word orange, orange, or red, right? But lemmatization is basically orangish, orangey, okay, and I don't know what else. If these two words occur, convert it to orange, right? So that is lemmatization. These are again pre-processing steps which occur a lot during before we feed something into the neural networks. Any questions still here? We are going to go to how neural networks handle text, which is aka dense encoding. We are going to go into the world of dense encoding. So before we go there, any questions in pre-processing and sparse encoding? Did that go too fast?
It's okay.
Okay. I hope everyone is on board.
Yes, Bruce.
Yes.
Okay, thanks. Um, Okay, so from here, we are going to talk about embeddings. And when I say embeddings, I'm going to mean dense embeddings. Okay, dense vector space, because purely technically, I can kind of call sparse representation as embedding, because I am embedding a word in a particular feature space. But now with Gen AI, the word embedding is usually reserved for embedding in a semantic space where the neural network has actually learned the context of the particular word. Okay, so embedding is going to be dense representation, dense vector space, right? So what embedding basically means is a dense vector basically places similar items near each other in a learned feature space. So doctor, patient, hospital, they are all very similar, right? Because they all they are all probably related to the medical world, right? The advantage of this kind of representation is this very famous equation where you have the word king minus man plus woman would be queen, right? So if you remove the maleness from the king and add femaleness or womanness into king, then it is queen, which is actually the feminine equivalent of king, right? So if you actually give something like this, your embedding vector can actually figure it out and it can give you an answer to this equation. So now how you have converted a simple word representation into kind of an equation, right? So again, I can say something like um, king minus money is equal to pauper, right? So it actually learns the semantics and how a word is represented, what meaning it carries, and all that, right? So let me just quickly make the case for what is an embedding space and what it looks like. So to answer, I think Niyaz's question is right here. The embedding vector space really is not human readable. Okay, so if we look at it, we really cannot understand what those numbers mean, because it is pre-trained, it has already happened, right? Like how the weights in a neural network hidden layer, they do not carry any meaning. It is similarly, the vector space also doesn't carry any, it has meaning, but you can't interpret the meaning as you would do in a bag of words or anything, right? So the word doctor, instead of it being represented as a single token ID or within a bag of words kind of a vector space, it is now represented in a dense vector space, right? So as a result, if I'm going to plot these words in some sort of my vector space, the word doctor, patient, and hospital would cluster together, whereas the word banana would be little far away. Right? And the network has learned it on its own. That this is the core of your embedding vector or your embedding space. That similar words will cluster together. Words with similar semantics will cluster together, and hence they are closer. They are related to each other. Is that clear? Okay. Oops, I didn't share my screen, right? Sorry. I'll just finish this part and then we can take a break. So I hope you can see the full screen. You can see the full screen version. Again, I'm sorry for the AI slop here. DVA classify visual deck. I never asked for it to say these things out loud. I only gave some text and asked it to make some slides for me. Okay, so can or does embedding occur after sparse encoding? Okay, so these are two different things, right? So, okay, just hold to your question in a minute and then we'll come to that. We'll come to your question, okay? After I'm done with this particular section, I think your question will be answered on its own. Okay, so we saw how a corpus is fed to if we want something like bag of words representation, that kind of vector representation, how the pre-training occurs. We saw that, right? Now, let's take a corpus and try to use neural networks for that. Okay, so simple counting words is not very helpful in a number of situations. I think I've made this case enough. So I'm going to just move to the next slide. The idea here is, see, it's teaching me how to teach, tell me who your neighbors are and I learn who you are. Okay, so that's what I'm supposed to say for this slide. But at the heart of it, that's exactly what a neural network is trying to learn, right? So it tries to see so it's kind of a sophisticated engrams or bag of words where it learns what words a particular word usually occurs with, right? So this is, let's say, my target word cat. I want to create a vector and a vector feature, a vector space for cat. Okay, I basically see what the particular word occurs with. So here is where I can go. I can see what is the immediate next word, what is the word that comes 2 words later, 3 words later. So I can decide that and I can let the neural network figure it, right? So basically, that's skip gram, right? How many words I want to skip in order to find what words co-occur with a particular target word. Okay. So I have the sentence the cat sat with a window size 1, cat, and then cat sat, and then the cat, and then sat cat. So I've basically created 4 different combinations, right? So cat, if my input is the word cat, then my next word is sat. If my input is the next word is cat. If my input is sat, my target word is cat. Okay, so what I am trying to do here is I'm letting the neural network learn the next word. Okay, so here basically I'm telling the neural network, here's my corpus. Okay, I want you to, let's go back to this couple of hidden layers. Okay, I want you to predict the next word. Right? So if my input word is the, my next word is cat. If my input word is cat, the next word is sat. If my input word is cat, my next word is the. If my input word is sat, the next word is cat. Okay. Now I am letting the neural network by using things like skipgram. Okay. And defining a window size. So sometimes in a sentence like this, I'm going to say, no, don't just look at the next word. Look at a window size of 2. Okay. So instead of looking the next word, go to the word that is right after that. So a corpus, small becomes corpus 1000 becomes or, right? So like that, it creates, humongous numbers of pairs, word pairs. Is that clear? That is the first step. My goal is to predict the next word. What word comes next? Right? The way I am asking the network to learn is, okay, look at the next word or the word that comes right after that. By using hyperparameters such as window size and how many words to skip and all that. Now, yes, Prince.
One means what? Does this means one word after my input?
What is it?
The window size equals to 1.
Window size is basically how many words I want to say. So I can take the cat. That is my window size.
So here,
skipgram would be how many words later I want to go.
Okay, so here because window size is equals to 1, so it means I'm trying to predict one word just after my input that I'm giving.
I'm trying to predict a word using one word.
Okay.
The target is always one word.
Okay.
That I'm not changing.
Okay. Thank you, sir.
Okay. So how would I actually train such a neural network? The first is I would do a simple one-hot encoding, my good old one-hot encoding, right? So here I have built a basic vocabulary. So the vocabulary actually identifies how many unique words are there. And for doing this, I have already done stop word removal. I've done some stemming. I've done some lemmatization depending on what downstream task I'm having. Okay. So my assumption here is all my running, all that is converted to run. Okay. Magnify, simplify, lessify, whatever, all that phi is removed. Okay, so it is all magni, simply, all that, right? The words such as the, was, is, but, all these are removed. Okay, I mean, depending on what stop words I give and what downstream task is there. Once I have this, let us say I have a corpus of 2000 unique words. I am one-hot encoding them. So I now have 2000 input values. Okay, high cardinal, that's okay. Right? By using some of these rules, which I have given here, okay, the window size or skipgram and all that, I'm telling your job is always to predict the next word. Right? So now see how from a rules-based approach in my sparse vector, I'm forcing the network to actually do a job. Okay. And in my output layer, I have a softmax, which is doing a 2000 category prediction. Why? Because I have 2000 words in my corpus. Out of these 2000 words, what is the most likely next word? is my softmax prediction that I'm doing. Right? So what goes as input, what comes as output, we are clear. Now what happens in my hidden layer? That is where that's where my kind of the magic is going to happen, right? Between my input and output, I'm going to have a couple of hidden layers where I'm defining the embedding matrix, where I'm going to say, okay, now represent the word cat using 128 dimensions or 50 dimensions, 100 dimensions, 1000 dimensions. That is a hyperparameter that I am giving to the neural network. Okay. Within that 128 or 50 dimensions that I'm defining, I'm forcing the neural network to come up with weights. Okay. Here I'm going to put soft max prediction. Okay, let us say I'm trying to my corpus has 2000 words, 2000 unique words. It is doing a 2000 class prediction. Okay, 2000 class prediction it's doing. Inside, I am giving a hyperparameter where I am saying represent this corpus using 50 dimensions. 50 dimensions. So I initialize the weights for these 50 numbers randomly, right? This is where your good old neural network algorithms, all the terms that we studied, starts coming into the picture, right? For these 50 dimensions, I'm going to say, okay, now the first dimension start with a random number of 0.5, second dimension start with a random number of root 2, third number start with a random dimension of 5000. Like this, I am doing up to n is equal to 50. That n is related to this n. Once I have initialized, okay, again, all my regularization, initialization, my Glorot initialization, all that I can implement here. Once I initialize, in the first pass, it is going to predict something, okay? The cat, dog is the next word. Now, it is also having the correct data, right? In the sense, the correct answer is sat. The cat sat. Okay, the cat sleeps. The cat runs. None of this is dog. The cat dog is none of these sentences that has occurred in my corpus. So it says dog is wrong, right? So the error score is high. Back propagation, weight updation, forward propagation. Now, instead of dog, it says the next word prediction is the cat runs. Oh, now this is a very good score. The no error, 0. Okay, back propagation. Next time for the word the cat, it is also the cat walks, right? So it is going to adjust the score accordingly because it now has 50 dimensions, right? Within the 50 dimension space, it is going to come up with the softmax score for each of this. So it is going to assign softmax score runs. The score is probably 0.8. Walks, probably 0.7. For the word dog, it is probably 0. Given the word the cat. This is my input. These are my output scores. right? So instead of one answer, it has figured out a set of possible answers, all represented by the vector space. All represented by this vector space. Okay, I'm not going to approve this. Fireflies.ai. I think the recording will be available in the platform. You can use that. Yes, Sam.
Yeah, Professor. Can this apply also to other languages like the Chinese character or Tamil language writing? Is it the
Definitely,
same thing?
definitely. All the languages, they work in the same principle, right? So it depends on how efficiently we do the subword tokenization. That's where linguists and grammarians, they come into the picture. They will say, okay, now you can break it at uncanny, unrepresentation, unhappy. So un is something, right? So only people with English knowledge will know that un is actually a subword. So that's where each language expert can do their own thing, the subword tokenization.
So
Yes, Bhadra.
from your experience, do you see maybe
Sorry.
do you see that English having a advantage over the Chinese character or having an advantage over, let's say, like Arabic or Tamil from your
I
experience?
I think with enough training examples, we can actually do any sort of language pre-processing. Any language neural training we can do. We just need lots and lots of examples. So with respect to that, um, I think if there are enough examples, we can build any neural network. I don't know Arabic, but from my interactions with Arabic people, they say that Arabic LLMs are very good. Whereas I personally find Tamil LLMs really not up to mark because by nature the dialect has different variations. There is like a classical pure form and then a spoken form. So the network really might get confused. So yeah, if there are enough training examples, you can train anything.
Enough corpus and like an example as in enough library of corpus.
Correct. Correct.
Okay.
If we have enough corpus, we can train any language. Yes.
Okay, thank you.
But
I think the same. It's the same question about the quality of the output for each language. This is my question, so I think it's covered now. Thank you.
Correct. So as long as there is some form of logic or it's correct. So the it can't be completely random, correct? There should be some form or some rules to what's happening. Okay. Yeah, Sam.
Before we go for the break, have this application be used on let's say animal communications between animals when they try to like dolphins to communicate with dolphins?
Yeah.
Have
We
they any
only
good
need yeah. So this is like understanding a dolphin language is as far as the neural network is concerned, it's just a translation task, right? So I translate stuff from English to Chinese, the same from English to dolphinese, if I can call it. We just need the golden answers, like what it really means. Are you going to put a mic to the dolphin and ask? Probably not. There are experts who actually understand dolphin communications. So they will give you a corpus like, this sound means this in English. So as long as that translation corpus we have, we can train anything.
Thank you. It's quite amazing.
Okay. There might be a robotic doctor. Probably, yeah. Yeah. Actually, you see these YouTube videos, which where they say, every sound has a meaning, like the way your cat meows. You can actually put a microphone next to your cat's meow, and there is an app which actually tells what your cat wants to communicate. There are apps which can do that. So at the
Wow.
back end, it's probably the neural networks
Yes.
and people who have actually done the translation, like convert, which they think is the correct answer. Animal psychologists, I mean, that's a whole field, right? So the subject matter experts, they give the golden answers for this. Yeah. Yeah, Leah.
Professor, before we finish today, could we give an update on the assignment within our WhatsApp
Yeah,
group?
sure.
There's some
Yeah.
concern that we're
It's
getting
pending. I
close
understand.
and we still don't have any direction. And so after break or before the end of the class, if you wouldn't mind giving us some
As I said, I've had a
clarity.
crazy week this weekend, but can I do it tomorrow first thing?
Yeah, whatever works for you, but
Yeah,
just to let you
ASAP
know,
tomorrow.
there is some
I
concern.
understand. I
Yeah,
understand.
thank you.
Thank
Thank
you.
you.
Yeah, I agree. With Adif, not sure I want my son's cat to know what he thinks of me. Definitely, yeah. If only cats could talk, right? Uh, okay. Okay. So after this step is done, I think we have covered this. Training means repeated prediction and correction. So we start with some random numbers for cat vector. And after many updates, it probably comes up with some numbers which actually represent the cat score, which gives a cat score. Now it's no more one number; it's like a vector, because cat in the context of Matt, it has a different meaning. Cat in the context of how cheeky it is, it has a different meaning. So yeah, all these things after many updates that happens. And within that embedding space that we discussed, what imaginatively, visually, what would happen is cat, dog, animal, car, mat, all these are like far apart in the embedding space. But hopefully, after training, cat and dog are closer to the animal or the word animal itself, actually, and little bit closer to mat than to car, right? Probably dog is more closer to car than cat. But the point is the distance becomes a little bit meaningful. Okay. I think we can take a break now and we can join back in 5-7 minutes. And then we'll just quickly finish this and start with the images. Thank you.